So in this video we're going to look at bivariate data. Now bivariate data is basically data which has two variables, from the word bi meaning two. So we're going to have a look at data with two different variables, and lo and behold, Blue Peter style, I have two variables here. So we've got the maths mark and the English mark of test, and what we wanted to have a look at is to see if these two are correlated. Now when you do correlation, and I'm going to do a few examples before actually doing this one, you've got a couple of options. You already know from key stage 3 that if I had a diagram that looked like that, it would be perfect positive correlation because it makes a straight line. And then basically as more points get added on the outside edge, you end up with positive correlation basically getting weaker and weaker until at one point, potentially, you actually have no correlation. And so you can't really tell. And on the other side of the scale, you have negative correlation. So as one variable goes up, so we'll look at, for example, IQ and wage. So in this graph, as your IQ goes up, your wage falls. In the previous one, as your IQ goes up, your wage goes up. And so these are the different types of correlation that you'll see. Now we're concentrating mainly here on just straight line correlation, but as you've seen in science at GCSE, you may not always get a straight line graph. You could get a logarithmic scale that you might need to use. So this is 2 to the power of x or something as the equation of my graph. I could also get a graph which looked like that, which, although having no linear correlation, you can clearly see there is some form of correlation. Now, generally speaking, in maths, we are going to concentrate on linear correlation. That's what we're always going to concentrate on. But in other subjects, you could get different types of correlation, which you'll then need to consider. And you can look at those in your set subjects. So we're going to concentrate just on linear correlation for the moment. Now, you've already had a look at your GCSE statistics. If you've done it, you don't have to have done it, by the way, but if you've done it, you'll have seen Spearman's rank correlation. Well, what we're going to do is we're going to look at the product moment correlation. And so we're looking at the product moment correlation coefficient and trying to find out effectively how well correlated things are. So what I'm going to do is I'm going to take this data and I'm then going to plot it in a graph. So as you can see, I've now taken these points here and I've plotted them in a nice little graph. So this is my graph for maths against English. And as you can see, there is going to be a correlation. It looks that as your math scores go up, your English scores go up. And what we're going to look at now is basically how we can then measure that. Because obviously we could sit there and say, well, hang on, there's a bit of a scale here. I think it's a pretty strong correlation. As one goes up, the other goes up. And that's effectively what we're going to measure. How strong is the correlation? Is it 1, incredibly strong, a perfect, makes a straight line, 0, no correlation whatsoever, or -1, again makes a perfect correlation, but this time negative, i.e. maths goes up, English goes down. So to do that, what we're going to need to do is plot a centroid point. And the centroid point is basically the mean of all my x values plotted against the mean of all my y values. So I'm going to add up all these numbers here, 20, 71, 60, 52, 80, so on and so forth, and find out what the mean is. And then I'm going to do the same for the English mark. So luckily, I did this in Excel, so I'm going to find the average of these scores and I'm going to find the average of those scores. And I'm then going to plot that point, which is 58.1, 59.6, onto this graph. So as you can see, I've now plotted that onto there, and what I've done is put a little red dot effectively where the center is. So this is 58.1, this is 59.6, and you can see there I've just put 2 lines in for it, and where they cross, that represents the very center point. So that point is called, I don't want to write in yellow in this, I'll go for red. So that is X bar, Y bar plotted just there. Now what we can tell now is we can have a far better idea of what the correlation is going to look like. Because actually if we then have a look at the values of our points, I can say, well, hang on a moment, compared to this, well, they're all in the bottom left and the top right. And so as a consequence, I am going to have positive correlation. If I had some points in the top left and the top right, then what I'm going to need to do is basically have a look at pretty much the average of them. Now, in essence, what I'm going to do in order to find that out is I'm going to look at this specific point here. So I know this point in my table is 7180. And so what I'm going to have a look and decide how I know that this makes positive correlation. Well, if I were to find, for example, the distance between that point and the mean there, so for this would be my y coordinate minus the mean of y, because remember these are the y coordinates horizontally. Then I was to say do the same thing with the x coordinate. So this time this would be x minus x bar. What I'd find is because this number is higher than that, this will come out to be positive. And again, for the y bar ones as well, because this is higher than that, this will come out to be positive. And a positive number times by a positive number will give me a positive region. And so in all of these ones here, what I actually find in region 1 is I find that all of them come out to be positive. If I do the same here, and again, I'm going to look at that distance and I'm going to look at that distance. Now I don't need the numbers just at the moment, but that is the bigger number, so that minus that will be negative. And same again on the other side, that take away that will be negative. And so what I end up with is in region 3, I end up with, again, positive numbers when I do x minus x bar times y minus y bar. Now if I took a random point, and I'll do this in black, if I took a random point here, then things would start to change. Because this distance horizontally, which is x minus x bar, well, that value is positive. But this distance here, which is y minus y bar, and this time notice the y coordinate would change because I'm on a different point, which is why I've done a different colour here. Well, that's actually going to come out to be negative. And so in my last region, which is region 4, everything, when you do x minus x bar, y minus y bar, will come out to be negative. And the same in region 3. Now because of that, I can have an idea, generally speaking, of what kind of correlation it is just by looking at this. But we can actually do it by using a proper formula. Because what I've done here is I've taken this for an English scale and a math scale which only go up to 100. Now, what happens if I do a different test and actually the score's out of 600 or 596? How can I compare the two? And so we need to get rid of the scale aspect in there as well. And to do that, what we're going to do is we're going to use a lovely little formula, which is for product moment correlation coefficient. R represents the correlation of an object. And the formula that we're going to use is going to be Sxy over the square root of Sxx times the square root of S, I've written it there, Syy. Now, just a little point on surds. This is actually exactly the same thing as writing it all under 1 square root. Why do I write it under 2? Absolutely no idea. I suppose it's the way I learned, and actually it just reminds me that this is a separate item to that, so I can work it out separately. So what we now need to do is think about what this Sxy, Sxx and Syy are. Now, for those of you that have had Mrs. Lipscomb, and I can't even remember which way I teach, it's been that long. For those of you that had Mrs. Lipscomb, she does use the Sxx form for using standard deviation. And so, in fact, I'll do the Sxx first because you've seen it before, potentially. So, Sxx, well, that is just the top half of your standard deviation. Because if you remember, your standard deviation was Sxx divided by n square rooted. And if you want to do, sorry, that's root mean square deviation. If you want to do the standard deviation as you know it, it is Sxx over n minus 1. This is the standard deviation for the population, which is why I've used the RMSD for those who've done S1. This is the sample deviation for the sample, which is why I've used the n minus 1. So the top bit on the line was sigma x squared minus n x bar squared. And so effectively, that is all that we need to do. Now, obviously from my table, I don't have all these values yet, but I'll end up getting them. So the next thing that I'm going to look for is SYY. Now SYY is the same thing, but this time I've replaced the X with a Y. Nothing more than that. And then the last one, SXY, well, that one's a little more tricky, but actually not too difficult. Because in essence what this is it's sigma X times Y. So X times Y, then add all the numbers up, minus N times, now X bar squared is X bar times X bar, Y bar squared, Y bar times Y bar, so XY will be X bar times Y bar. And so these are the three formulas that you're going to need to remember, which will prove invaluable. So actually working them out, well, if you have a look at the example that I've done in example 4.1, you'll see how they actually get worked out. I'm just going to pause all, well, in fact, I know, I'll just do it now. So if we call the math mark X and the English mark Y, I'm going to need a column for XY, so that times that. I'm going to need, what else did I need? I need to know how many there are. I need to know the sum of X squared, so I need a column for X squared, and I need a column for Y squareds. X squared is that squared, Y squared is that squared. Copy them all down. Sum them all up. Oh no, that's the average, isn't it? So let's sum them all up. And so there are my values. And I can now use these values in this lovely little formula. So sigma xy was 3841. So sigma xy equals 38481. Then sigma x squared came out to be 38279. Sigma y squared, that's an awful sigma, that one, comes out to be 39124. Then I also need to know how many things there are, so n, and I can look down here, there turn out to be just 10 of them. So n is 10. So the next thing I need is x bar and then y bar, and then I should be good to go for everything. Now x bar we've already worked out because I've plotted it on the graph. That was 58.1. And y bar was 59.6. And so now what I can do is plug all of these into my calculations. So what I'm going to do is just move a little bit to give me some space for working. So there are all my values filled out. Now again, you don't necessarily need to do all of this yourself. Your calculator will help you. Obviously the key bits that I want to see for just exam purposes, 1, your formula, 2, your numbers put in, 3, your answer. So you are going to write all of this, but the calculations themselves, actually you'll be able to put into your calculator. And again, I'll do a little video for that later. So what I'm now going to do is work out the product moment correlation coefficient. So that is SXY over the square root of SXX times the square root of SYY. Again, could be all over one square root if you wanted. So I'll then fill all the rest of that out. So there's my little value, 0.955 to 3 significant figures, and that is the product moment correlation coefficient. Now remember back to the scale that I was talking about. If you have a scale where your coefficient is -1 and you go all the way to 1, and obviously in the center you have 0, this one at the top would be perfect positive correlation. This one at the bottom would be perfect negative correlation. And this would be no correlation. Now obviously there's scales in between, and to give you an idea of what the scales look like, I've got something just here. So just as a little final for this, here's a little tool showing the correlation coefficient with R. They've got IQ versus job performance. So here we've got perfect correlation, 0.9, 0.8, and you can pause it to have a look. As you can see, by the time you get to 0, pretty much there's no correlation. Now do bear in mind we're always talking about linear correlation, but that shows effectively the difference between moving from R as -1 to +1. Obviously it's not perfect because it's just an example, but it gives you an idea behind it.